Jablonski diagram. The present title is related to the topic photochemistry. Photochemistry deals with the study of chemical reactions caused by light radiation. The light radiation applied in photochemistry may be visible or ultraviolet radiation whose wavelength ranges from 800 nanometer to 200 nanometers. Generally, in chemical reactions, the reacting molecules acquire energy. They need some energy for the formation of products. The energy may be heat energy, light energy or mechanical energy. Light energy is provided by light radiation. Light radiations exhibit dual nature, dual behavior. They have wave nature and particle nature. The particles of light radiation are called as photons. The reactant molecules absorb only photons from light radiation. Each photon carries an energy equal to one quantum, that is h nu. The main aim of this presentation is to get a clear understanding about two phenomena. One is fluorescence, another one is phosphorescence. They could be explained with the help of Jablonski diagram, which is a diagram, a pictorial representation of various happenings which occur during the photochemical reactions. For better understanding Jablonski diagram, we need to familiarize ourselves with certain terms or definitions. They are spin of an electron, total electron spin, spin multiplicity, ground state, excited state, singlet excited state, triplet excited state. First, we shall see spin of an electron. We all know electrons are atomic particles. They present in every atom and they are revolving around the nucleus of an atom. Electrons are negatively charged particles and all electrons are under constant spinning moment. What is spinning? It is nothing but revolution of an object in its own axis is called as spinning. Because of this spinning movement, each electron acquires a spin value. The value may be plus half or minus half. During clockwise spinning, they acquire the spin value of plus half, and during anti-clockwise spinning, they acquire the spin value of minus half. Spin value of an electron is represented by the symbol small s. The next term is total electron spin. This is represented by the symbol capital S. Total electron spin is the sum of spins of all electrons present in the atom. Generally, all molecules want to be present in the ground state. Ground state is the energy state of very minimum energy. In the ground state, electrons want to present as paired. That is a set of electrons. Each pair comprises two electrons. This is possible. This pairing is possible only if the two electrons in the pair have different spins. That is, one electron must be with a spin value of plus half. Another electron must be with a spin value of minus half. If the electrons are in the paired state, then the net spin value will be 0. That is the total spin, electron spin, total electron spin S is 0 in the paired state. The next term is spin multiplicity. We can calculate the spin multiplicity with the help of the formula 2s plus 1, where s is the total electron spin. When the total electron spin is 0, that is when all electrons are paired, total spin will be 0. Then the spin multiplicity is 1. If the spin multiplicity is 1, the molecule is said to be in singlet ground state. Singlet ground state is represented by the symbol capital S with a 0 in the suffix. That is S0 or S0. Now we are entering into the photochemical reaction, and now we have to apply Jablonski diagram here. During photochemical reaction, the molecules absorb light energy in the form of photons. Because of absorption of light energy, one of the electrons from the pair which are present in the ground state will go to higher energy state. Higher energy state is commonly called as excited state. Now, in the excited state, that single electron may have a spin of plus half or minus half. If its spin is plus half, then the total spin S will be 1. Here we are considering that the electron in the ground state has a spin of plus half. And in the excited state also its spin is plus half. So the total electron spin is 1. Now let us calculate the spin multiplicity. Let us apply the formula 2s plus 1. Here s is 1. So 2 into 1 plus 1, which is equal to 3. That is spin multiplicity is 3. In this situation, the molecule is said to be in triplet excited state. Since one of the electron is excited to higher energy level, and since the spin multiplicity is 3, the molecule is said to be in triplet excited state. These processes are represented by this diagram in this slide. That is, this is the ground state. Here the electrons are present in the paired fashion. That is, one electron is in undergoing clockwise spinning moment, another electron is undergoing anti-clockwise spinning moment. The spinning moment is represented by arrow in chemistry. We all know that. By absorption of light radiation, which is absorbed in the form of photons, one photon is equal to h nu. One of the electron from the ground state gets excited to the higher energy state. Two chances are there for the electron in the excited state. It may have a positive spin value, that is plus half, or it may have a negative spin value minus half. If it has a positive spin value, then the total spin will be 1. So the excited state is represented as excited triplet state, that is triplet excited state. If the spin of the two electrons are opposite, then the total spin will be 0. Then the multiplicity will be 2s plus 1, that is 1. Now the molecule is said to be in singlet excited state. This is given in the next slide. That is, if the excited electron has a spin value of minus half, total spin will be 0, spin multiplicity will be 1. Now the molecule is said to be in singlet excited state. Here we have to talk about the next stage of photochemical reaction. The molecules have the tendency to absorb 1 quantum of radiation, 2 quanta or 3 quanta. The amount of energy absorbed differs for different molecules. Some may absorb 1 quantum of energy, some may absorb 2 quanta or 3 quanta or 4 quanta, etc. Depending upon the amount of light energy absorbed, they may go to, the electron may get excited to different energy levels, different excited energy levels. Correspondingly, we have different excited states. That is, we have a series of singlet excited states and a series of triplet excited states. The series of singlet states are represented as S1, S2, S3 and triplet states as T1, T2, T3. S1 is called as first singlet excited state, S2 second singlet excited state, S3 third singlet excited state, and so on. Similarly, T1 is first triplet excited state, second triplet excited state, and so on. Generally, another point we have to know here is the energy of singlet excited state is always higher than triplet excited state. This point is also important for studying the Jablonski diagram, for analyzing or understanding the Jablonski diagram. This is our Jablonski diagram. Here we shall see the ground state represented as S0 as we have seen earlier. S1 is first singlet excited state, S2 second singlet excited state, third singlet excited state, and these are first triplet excited state, second triplet excited state, third triplet excited state. Always S1 state has higher energy than T1 state and S2 has higher energy than T2 state. That is, triplet states are lying at a lower energy level than their corresponding singlet states. Here, light energy is absorbed by the molecules in the ground state. They may go to S1 state, S2 state or S3 state, and they will return back after some time. The return process may be from S3 to S2, S2 to S1, similarly T3 to T2, T2 to T1. From after attaining S1 or T1, they return back to the ground state. If the return back is from S1 to S0, the process is called by the name fluorescence. If the return back is from T1 to S0, the process is called or represented by the name phosphorescence. We shall see in detail about fluorescence in phosphorescence in the forthcoming slides. Molecules absorb light radiation in the form of photons. They get excited to the singlet or triplet excited state. In the excited state, the molecules are called as activated molecules and represented by as A star. A naught is normal molecule, A star is excited molecule. Now let us analyze the return process, that is what is happening during the return travel of molecules from the higher energy state, that is activated state, to the ground state. This return process occurs in three ways. One is non-radiative transition, the second one is radiative transition, the third one is chemical reaction. Let us discuss one after another. The first one is non-radiative transition. Here, the return process occurs from higher energy excited states, that is S2, S3, S4, etc. to the first excited state, namely S1 or T1. During these transitions, return process, return travel, there is no emission of radiation. The excess energy is dissipated only in the form of heat. This return process will occur in two ways. One is internal conversion represented as IC, another one is intersystem crossing represented as ISC. During internal conversion, both are return processes, and during both the processes there is no emission of radiation. That should be kept in mind. Only the way, the route, the transition is different. During internal conversion, the transition occurs in between, only in between S states or T states. There is no transition from S to T or T to S. That is, transition is from S3 or S2 to S1 or T3 or T2 to T1. And this process occurs in a very less time of the order of 10 power minus 11 seconds. The another one, intersystem crossing, here there is transition, possibility of transition from different multiplicity states. That is, transition is possible from S to T, and that is S2 to T2 or S1 to T1. Actually, this transition is considered as spectroscopically forbidden transition, and though forbidden, it do occurs to some extent. This transition occurs at a very slower rate. It requires some time. This transition requires some time. These are represented in the Jablonski diagram by the symbols IC and ISC as we have seen earlier. The next one is radiative transition. This slide is very much concerned with our title Jablonski diagram, because we are going to discuss about the two phenomena, fluorescence and phosphorescence, by using the content of this slide. When the transition is, that is, transition means return back process from S1 to S1 or T1 to S0, that is ground state. There is emission of radiation, there is emission of light radiation. This transition occurs in two ways, that is, S1 to S0 may occur or T1 to S0 may occur. Both the return processes end up with the ground state, that is S0. If it occurs from S1, then it is called by the name fluorescence, that is fluorescence. If it occurs from T1, then it is called as phosphorescence. We already know the molecules are in return back to S1 state and T1 state. The molecules are now in S1 or T1 state. So we are dealing only with the transition to the S0 state, that is ground state. It may be from S1 or it may be from T1. If it occurs from S1, it is called fluorescence. This fluorescence occurs in a very less time of the order of 10 power minus 8 seconds. Another important point to be noted here about the fluorescence is this process is accompanied by emission of radiation, and it ceases as soon as the light source is cut off. And the important point to be known about the phenomenon of phosphorescence is it is also accompanied by emission of radiation. It occurs or the phosphorescence, the process, the phenomenon phosphorescence needs more time than fluorescence. That is, it occurs in 10 power minus 3 seconds, compared a very long time compared to 10 power minus 8 seconds. it occurs very slowly. Why phosphorescence needs more time? Because phosphorescence is transition from T1 to S0. T1 is triplet state, S is singular state. In T1 state, the electron is in with is under clockwise spinning moment. If it has to come back to S0, it has to change its spin. That is, spin inversion has to occur, because we have already considered that in the ground state the electron is present, the single electron is present with the clockwise rotation, clockwise mode of spinning. If the electron in the triplet state wants to paired up with another electron in the ground state, it can get paired up only if its spinning moment is in opposite direction, that is anti-clockwise direction. Otherwise, the pairing will not be possible. So that spin inversion must occur in the T1 state itself. Then only it can come back to S0 state and get paired up with another electron already present in S0 state. This spin inversion requires more time, so that phosphorescence is said to occur in 10 power minus 3 seconds. But this transition is said to be a spectroscopically forbidden transition. Now we got a clear understanding about the mechanism of the phenomenon fluorescence as well as the phenomenon phosphorescence. Again, I am insisting, I am reminding the point about phosphorescence. It will occur for a long time and it will continue, or it will extend, the emission extends even after the light source is cut off. In the case of phosphorescence, it is to be kept in, these points must be kept in mind. The point immediately that should be come to our mind about fluorescence is there is emission of light radiation, it is a faster process and it ceases as soon as the light source is cut off. The points that should arise in our mind as soon as we heard of the term phosphorescence is phosphorescence occurs at a slower rate. There is emission of light radiation, but the emission extends for some time even after the light source is cut off. The third way of loss of energy, loss of absorbed energy from light radiation is chemical reactions. Usually chemical reactions occur if the molecules are in triplet excited state, because in the triplet excited state the molecules spend very much time, they spend more time in the triplet excited state in order for inversion, spin inversion. They need to get the spin inverted to come back to the ground state, that is S0 state. During that long time, molecules have chances to undergo chemical reactions, so that transition from T1 to S0 may be accompanied by chemical reactions also. And the transition from singlet excited state, that is S1 to S0, never lead to chemical reaction, because it occurs very quickly. The molecules have no chance for the formation of products. I hope with this explanation I conclude the presentation. Now I hope this presentation may be helpful for getting a clear understanding about photochemical reactions. What are all the processes that are occurring in photochemical reactions, how the photochemical reactions are executed with the help of photons absorbed by absorbed from light radiations. Thank you very much.